So if you're watching at home, in this video, we're going to talk about solving some inequalities, and this is your warm-up for this lesson. So if you're watching at home, pause your video. We're about to go over this here in class in real time. So pause the video, give yourself some time to work it out, and then push play when you're ready to discuss. You guys that are here in class, let's go ahead and start discussing. Number one, and I'm just going to go around. This is going to be a little Q&A style kind of session here. Paul, I'll start with you. Paul, what is the, if you were going to describe what kind of function is in number one, what is it? Very good. It is a quadratic function. Okay, Lewis, what is the shape of a quadratic function? Very good, a parabola. So when it says list any intercepts, okay, what are the two types of intercepts, Tiago, that one must consider? X intercepts and Y intercepts. Now, class, listen very carefully. You're going to get a true or false question. This might be an exam question. Hint, hint, wink, wink. True or false? Every quadratic function has an X intercept. James, you shook your head. You said false. Describe for me a quadratic function that does not have an X intercept. If the vertex is above the x-axis and the curve is, how would we describe a curve that looks like this? Concave up. Excellent. True or false? Every quadratic function has a y-intercept. A little more contention on this one. It is true. And I'll tell you why. Because the domain of a quadratic function is all real numbers. No matter what the quadratic function is, you can always plug in x equals what? X equals 0. Good, Will Edwards. Because that is how we find the y-intercept, isn't it? We plug in x equals 0. And so to do that on part A is quite simple. I would just, with part A, I would say, all right, what is f of 0? And you guys would tell me, oh, well, f of 0 would be 7. Took us too long to do that. You're plugging in x equals 0. That's the cover-up principle. Cover up the x terms because you're plugging in x equals 0. Those go away, and you would be left with nothing but y equals 7 there. So that constitutes the y-intercept. George, is this one going to have any x-intercepts? Oh, rats. George, you are the man. Thank you so much. These boys at home watching, if any, are watching me, but you did not see that. So when I did cover-up principle, literally what I was doing was covering up those x terms again, so you could see the y equal to 7 there. George, how do I go about finding the x-intercepts? Oh, very good. So in other words, to find the y-intercept, we let x be 0. To find the x-intercept, we let y be 0. Okay? So if I let y be 0 or f of x be 0, I'm solving this quadratic equation. Plus 6x plus 7, which means that if I were to, let's say I were to add x squared to both sides, subtract 6x from both sides, subtract 7 from both sides, sort of switch things around, this is a quadratic equation, and read how many solutions does every quadratic equation have? It has 2 solutions. Okay, this is a little exam review for us, boys, right? We're going over some stuff that we've talked about throughout the year, and George had the great idea to factor this. Okay, so I would like for Ben to go ahead and factor it, please. Beautiful. X minus 7, x plus 1. We check it by foiling, and then we get with the ZPP, and we see that x equals 7, or x equals -1. So those constitute the two what on the graph? The two x-intercepts. All right, and so accordingly, I'm going to say here's a point 7, 0. Here's another point -1, 0. So what we're doing is we're putting together a list of intercepts, all for number 1. Okay, now I need some more room, so let's scoot this down, and let's scoot these two guys down. All right. So part A is complete. I've got my intercepts. In blue, I've got my y-intercept. In red, I've got the aforementioned x-intercepts. They don't necessarily have to be there, but in this case, they are. We didn't mention this, but can you speak, Will Edwards, to the concavity of this function? It is concave down, that leading coefficient test, right? A is -1, so this is swole patrol all the way. Concave down. All right. It says give the equation of the axis of symmetry in part B, and it says give the coordinates of the vertex in part C. All right. I'm a visual person, so to help me do that, I'm going to go ahead and sort of put down on the graph what we've got thus far. All right, so 0, 7. 1, 2, 3, 4, 5, 6, 7. There's 1 point. 1, 2, 3, 4, 5, 6, 7. There's another point. There's another point. So like right now, what we've got is we've got these 3 points. Now there's a vocab word. If all 3 of these points were on the same line, what would they be? Paul? They would be collinear. Now, of course, they're not collinear because this is not a linear function, is it? It's a quadratic function. They're all on the same parabola. Now, in part B, I mentioned this phrase axis of symmetry, okay? Joey, talk to me a little bit about symmetry. What does symmetry mean in this context? Yeah, very good. I have used, self-deprecatingly, I have used the example of my face is not very symmetrical, right? If you cut my face down the middle, the left side and the right side don't exactly match up, right? But with a parabola, it does. So where would we, quote, cut our parabola down the middle? Oxford. Jake is absolutely right. Split the difference between the x-intercepts. You've already found the x-intercepts, right? Joe, what's the distance between those two x-intercepts? How far apart are they? They are 8 units apart. So if I split that in half, I get 4. So my axis of symmetry must be at x equals 4, right? Grove, how dare you shake your head? Why not? Yeah. The 4 is that I mentioned, it isn't the location of the axis of symmetry, it's the distance from each of these particular points, right? So very good. I was trying to trick y'all and y'all wouldn't be tricked. So I'll just sketch my axis of symmetry right here. It's a vertical line. That ought to do it for right now. And on this vertical line, we know that the curve will have one point called the vertex. The vertex is the point on the parabola that is also on the axis of symmetry. All right. Now, where would you say should my vertex be down here? 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 Why not? What's wrong with all those places? Yeah. What do we know about the vertex, Alex? Well, in this case, it's going to be the highest point on the curve. It's going to be the mountaintop, right? If the parabola is concave down, the vertex is the maximum, the highest point. If the parabola is concave down, concave up, then the vertex will be the bottom of the barrel. It will be in the valley. It will be the minimum, the lowest point on the curve. All right. Now, noting that this parabola is symmetrical, I'm going to put another point. I'm going to put a 4th point right up here to match with the y-intercept, right? So we have these two x-intercepts symmetrically placed. These two are symmetrically placed. And so I probably, if I wanted to put my finger on it, maybe right up in this region somewhere, okay? The equation of the axis of symmetry, before we actually get to the coordinates of the vertex. The equation of the axis of symmetry, we noted, is a vertical line. Charlie, what do all vertical lines look like as far as their equations? They got something in common. X equals a constant. Very good. It's X equals a constant. Okay, Nate, what is that constant for this particular example? X equals what? Look at the picture. Where does it cross through the axis, the x-axis? Where does my dotted line cross through the x-axis? 3. Good. 3, 3, 3. So anywhere I go up and down this line, it doesn't matter what the y value is. The x value is constant at 3. So a vertical line, as Charlie said, has an equation of x equals 3. What does that mean that a horizontal line Luke would have an equation of? Y equals a constant. Okay? Y'all remember about linear functions? Okay? So I know now that my axis of symmetry is going to have an equation of x equals 3. Okay? So that's the equation of my axis of symmetry. And so how do I go about finding the y-coordinate of my vertex? Because I hope you know we've already got half of the vertex. We've got vertex 3 comma something. So we already know half of the vertex because we split the difference between the x-intercepts. So how do I know how high up to go? How do I find the corresponding y value? Will? Not Will. Shoot, Jack. I did that again. I hadn't done that in a few months. Jack? Oh, that's interesting. Why do you say that?
Well, because on both sides, it's going up by 7 towards the axis.
All right, so Jack is thinking along the lines of rise and run, slope, in other words, okay? All right, so I love you, Jack, but you wrong, brother. A parabola does not behave in a linear fashion. A parabola will not, for example, just because we go up 7 into the right one, doesn't mean I can continue to go up 7 into the right one, up 7 into the right one, or else it would be like a jagged line, it would be more like the absolute value graph, okay? But that's not a bad guess. We are looking at patterns. We're trying to figure that out. So, Tiago, what do you think? How do I find the y-coordinate of my vertex? How high up the dotted line should our vertex go? Or whatever you wanted to say. You had a hand in the air, so I call on you. You gonna pass it off? Absolutely, absolutely. That's exactly what we want to do. Well done. So if I'm going to find the y-coordinate, remember, f of x is the same thing as y. So it's like saying, well, gee, y equals the opposite of x squared plus 6 times x plus 7. And so if I want to find the y-coordinate, dadgum, just say f of 3. What is f of 3? Figure out what f of 3 is, and that's your y-coordinate. All right? So let's see, we do this in our head, I bet. -9 plus 18, that's 9. 9 plus 7 is 16. So we get y equals 16. Now, boys, I'll be honest with you, I really don't want to make 16 tick marks. So I'm just going to kind of cheat, and I'm going to put this up here, and we're going to call this 3 comma 16. Okay? Truth be told, you don't have to make tick marks if you're graphing these out. You could just, as long as you know the coordinates, you're fine. All right, so the vertex we've done, let's see here. Check, check, check. And then here we go. I'm going to curve this down. That's not terrible. I missed my mark a little bit. Curve this down. All right, so that's a pretty decent little parabola, okay? And then what in the world with part D? What is part D asking? It says solve f of x equals -9. How in tarnation do I do that? Do what, Jake? Plug in what? It's not saying what is f of -9. It's not saying let's figure out what the y-coordinate is over here when x equals -9. It is saying what x-coordinate or coordinates, dun, 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 what x-coordinates would produce an output, a y value of -9. So in other words, it's like coming down here and saying 1, 2, 3, 4, 5, 6, 7, 8, 9. It's like saying, hey, whoops, missed. Where will our parabola hit? Right? Where will our parabola hit down there at the line y equals -9? Luke a moment ago said horizontal line is going to have the equation of y equals constant. So this is like now we're like trying to figure out, well, where's it going to hit down here? Okay. Somebody in my freshman class yesterday said, Coach Warren, where do you see parabolas in the real world, in everyday life? And I said, man, you see them all over the place, right? Anytime you have a projectile that's in motion, it's following a parabolic path. So like if I shot an arrow, Betsy, my 8-year-old daughter, is learning how to shoot a compound bow. She's got a nice pink Genesis bow that she loves shooting, and so she is learning to control the parabola, so to speak. Okay, and so like if Betsy is shooting her little compound bow, that cute little pink bow, and here's Betsy, and she's got her bow, and she's got that arrow, and it's going to go woo right there at the mark. Okay, that's a parabola. It's going up and then down. And so figuring out things like, all right, well, when's it going to hit? Like, let's say her target's over here, or let's say her target's up here. Let's say she's in a deer stand with me and her target's down there. These are all quadratic questions. And so figuring out when is my function, to get back to this warm-up, when is my function going to hit -9? I want to set the equation equal, not to 0 as we did earlier, to find the zeros or the roots or the x-intercepts, but I want to set it equal to what? I want to set it equal to -9. Okay? And I reckon we can do that. Let's do that. So -x² plus 6x plus 7 equals -9. Now, Andrew, we have talked about 4 strategies for solving quadratic equations like what I just wrote up in black. Can you name 2 of them? Graphing and completing the square. Good. James, can you name the other 2? Pardon? Quadratic formula. We used this in red. Yeah, factoring in the ZPP. Good. So so far this year, we've talked about those 4. Graphing, factoring the ZPP, complete the square root method, and then quadratic formula, okay? You are free to use any one that you want, just as long as you keep your head on straight, okay? Quentin, we'll let you choose. How do you want to solve that black equation right there? You said louder. I couldn't hear you. Factoring and the ZPP. All right. So this is the zero product property, which means I need to set everything equal to 0. So let's see here. We got -x² plus 6x. I would add add 9 to both sides and get plus 16 equals 0. I don't like negative leading coefficients, so I'm going to multiply everything by -1. So -16 equals 0. And then Mossy, can you factor that for me? Can you pick 2 factors of -16 that add up to -6? So x, 2, 8. Does 2 plus 8 equal 6? Does 2 plus 8 equal 6? Does 2 minus 8 equal 6? What kind of 6? A -6. So we're good on the 2 and the 8. I need you to help me figure out my signs. Should the 2 be positive and the 8 be negative, or vice versa? What would you like? Very good. So the 2 needs to be positive, the 8 needs to be negative. Again, we check it by doing what, class? Foiling it out. All right, so my answers here would be x equals -2 or x equals +8. Now, is that in line with my picture? So this point right here would be -2, -9, and this one would be 8, -9. And so we have solved part D. Now, look, we just took 20 minutes to talk about one problem. I know that. And it's a warm-up problem that I gave y'all like, maybe 3 minutes to chew on. But it's a great summary of a lot of the math that you guys have been practicing and learning with me this year, right? So dealing with a quadratic like this, just a quadratic function, and being able to answer questions about intercepts, about roots, about axis of symmetry, vertex, and all that good stuff. That is a necessary skill for any Algebra 1 student to have mastered, okay? Have y'all started doing any work with quadratics in y'all's classes yet? Y'all graphed any parabolas, perhaps? Okay. Let me. The reason I asked that is let me pretend like, okay, pretend like I haven't taught you jack squat about axis of symmetry, X intercepts, Y intercepts, vertex. I've taught you nothing about parabolas, and I just give you this function right up here, and I say, hey, would you please graph this function? What would you do to put together a picture of a new mysterious function that we haven't ever heard about before? Jack McBee? Quentin? Leave the class, take the L, dead gummit. I will give you a great piece of advice then. Make an X and Y chart or table, right? Pick some X values, plug those X values in, get the corresponding Y values, and then play connect the dots. That is how we graph, quote, any new function that we haven't dealt with before, okay? For example, okay, I'll put that to the test here. I guarantee you, you'll be able to graph a new function that you haven't ever seen from me before. Y equals 2 to the power of X, okay? If you make a table of values, you will be able to graph out any new function that you can analyze. So like, for example, what are some smart values? Should I plug in X equals 15? 2 to the 15th is a ginormous, gargantuan number. I'm not going to make that many tick marks. That's not helpful, right? But maybe 2 to the 0, 2 to the 1, 2 to the 2, things like that, right? So 2 to the 0, 2 to the 1, 2 to the 2. So here's my input, here's my output. Class, what is 2 to the 0? And what is 2 to the first? And what is 2 to the second? And what is 2 to the third, just for one more? 8. Okay. So now all of a sudden, we plot things out like this. There. 6, 7, 8. And there. And we think, ooh, that's kind of cool. But, it's tending, I was making my numbers go to the right, and it's going straight up. I wonder what happens. Pardon? Yeah. I wonder what happens to the left, to the left, to the left. All right, so in other words, plug in -1. Here's where it gets interesting. What's 2 to the negative first power? 1/2. Somebody said it. Was it you, Alex? 1/2. Now, you call baloney on that one. You say, wait, oh, come on, Coach Moore. No, take up, try it. Look, what's 2 to the negative first power? We know that with a negative exponent, we put 1 divided by that raised to that positive exponent. So it's 1 divided by 2 to the positive first, or just 1/2. What does that mean I get when I plug in -2? 2 to the negative second is 1 over 2 to the positive second, which is 1/4. Okay, do you see the benefits? Here, let me see if I can squeeze in 1/2, 1/4. And now all of a sudden, what's it doing as it goes farther and farther to the left? It's getting closer and closer to the x-axis. And then you connect the dots. Congratulations, you guys just graphed your first exponential curve. Exponential growth, right? Hogan, y'all be quiet out there, please. I'm hearing about hash browns and y'all are making me hungry. So what's the main lesson here? Not to learn how to graph exponential growth. It is to figure out that if you have a newfangled function that you're asked to graph, make a what? make an X and Y table. Boys, you will be doing that. I know I've said this already in this class. I know I've said it already in this class, but it might have gone in one ear and out the other. So write it down if you didn't write it down. That look, you're going to be doing this kind of process for the next 4 years. Your teacher, Mr. Perry, Mr. Higginbotham, Mrs. McConnell, Dr. Giroge, whoever you have is going to say, here's this new function. Let's discuss it. Let's figure it out. And you'll be making an input and output table. You'll be seeing, well, how does this function relate to big X values, to little X values, whatever. All right, so like the reason I say that is because look at number 2. We aren't even going to get to number 3, but that's okay. Look at number 2 here. Now that's not a new function, but if you just had a brain fart and you forgot all about absolute value being a V, right? And you forgot how -3 on the inside shifts it to the right 3 units, and +1 on the outside shifts it up 1 unit, and multiplied by 2 vertically stretches it, right? And if you forgot all of that, you can still make a what? An X and Y table, okay? So that unlocks the door for a problem like this, okay? Like if you were going to be graphing a function out loud. I know you're not supposed to be graphing this one. You're supposed to be solving it. I'd subtract 1 from both sides, divide by 2 on both sides. What's that going to give me? 11. So absolute value of X minus 3 equals 11. That means that X minus 3 is a number that's 11 spots away from 0. I could go to the right, or I could go to the left. So X minus 3 could equal -11, or X minus 3 could equal +11. And then let's just add 3 to both sides. So X equals -8, or X equals 14. And that's an absolute value equation. Real straightforward. We talked about that back in August and September. Any questions on number 2? Okay. Do we have time for our last one? Do y'all mind if you're maybe a minute late? Are your teachers going to be mad and grumpy? No? All right. So what type of inequality is this? Who said that? Lewis, you dirty dog. It is linear. Very good. Then a boy. So it's a linear inequality. It is of the form y equals mx plus b, right? Joe, what does that mean that my slope is? Good googly moogly, boy. Y equals mx plus b. What is the slope? Yes. So in that example, it is what number? Good. That's your slope right there. Okay. Paul, what does the 1 stand for? The y-intercept. Fabulous. Okay, so we got our slope. We got our y-intercept, our yint. The y-intercept, this is all hacked at this point, hopefully for you guys. The y-intercept is where we would hit the y-axis. We're going to go, a slope class is blank over blank. Rise or run. So we go up 2. Y'all are like, oh, finally we're on comfortable ground. We've been dealing with this in our classes. We go down 2, or to the left, and to the left 3. So there we go. Those 3 points are very good. Collinear. Somebody said over here. Those 3 points are collinear. Now, what kind of line, George, should I draw here? Solid or dotted? Because of that strictly less than sign, right? So we're going to make a dotted line. Okay, and in class, where should I shade? Above or below? Below, because it was y is less than. And that's where all of our y values that are less than are found. Okay, so hey, wonderful job today. We didn't get into any of the lesson, but this was a great review for us. Your exam, you need to be studying for right now. Okay, your exam in about a month. It would be fabulous. Study a little bit every other day. Don't try and cram at the end. Tiago. I do not, but I can find that out. I'll look on my calendar and actually ask y'all's parents if y'all's calendars at your school, if it's like, oh, we're going to be going to Washington, D.C., or we're going to be doing this or that. I don't know. If there's any dates that y'all are going to be gone, or maybe your last day of school, y'all send me those dates. And have a wonderful day. Live Jesus in our hearts. All right, fellas. Thank you so much. Great work. Your last day is May 11th. All right. All right. End meeting.